Hi there, welcome to your practice test on vector and deductive geometry proofs. Hope you've done some revision. Proving stuff can be fairly challenging. Now this test has got 6 questions and a total of 38 marks. So just put that over here, 38 marks, which in the SACE program should be about 45 to 50 minutes, usually allowing about 1.2 minutes a mark. Okay, so here we go. Put your name on it. You might be working off screen there and just putting on a piece of paper or whatever. The process is this. Here's the first question. You pause the presentation, have a go. Then I'll scroll down to the rest of that question, then onwards through all the questions. Now I want you to stop the presentation, check your work, because if you continue, I will go back to question 1 and do all the solutions on screen. So not only will you have the answers, the solutions, but you'll see how to work them out. All right, okay, away we go. Start your clock now. Give yourself about 50 minutes. Here's the first question, 1 part A. Pause it, have a go. Let's go down to B. So you might have to scroll back, prove that AB equals BC. It uses the same diagram. So you might have to go back there. Let's go on. Question 2, this diagram there, part A. Pause it, have a look, see what you can do. Part B. Question 3. Part A there. Then part B. Now, put a note here for myself. See that sign, that absolute value sign? We don't need it. That one in front of the bracket. Don't need that one. So I should have watched that. Okay, let's go on. Question 4. And part B. Question 5. And it's part B. Same diagram. And finally, question 6. This one's screen clip from Hayes and Harris publications. Okay, so that I thought it was a good one for a vector type proof. All right, have a go now, pause it, check your work, because I'm going to show you the answers now and the mark scheme, so you can see how to do it and what each point is worth. Here we go, we're going to go back up to the top now, and let's have a look at some answers. Okay, I'm going to give you some strategies as well. So BC is the tangent, just reading that, so watch this, perhaps underline it. AB cuts, so that's all right, angle ABC is beta, yes, they've marked that, we've got to make sure you mark all the stuff in, and CB equals BD. I think we should put that there so we don't forget it. That's the first strategy. Read all the given information and make sure it's recorded on your diagram. Now we want to prove that angle BAC, so that's this one up here, is pi minus 2 beta. Okay, well let's see how we can go. How we go. Now first of all, I think the good strategy is to use each of the given piece of information in turn. So what can we say? Let's use the isosceles triangle. So we can say CD equals CB. That implies triangle CDB isosceles. Therefore, angle CDB is also beta. This one in here. Why? Base angles. Okay, that's enough. We've set it isosceles. So we use that first bit of information, CD equals CB. What's another piece of information we haven't used? This one here. It's a tangent. Can we use that? See how it's quite commonsensical how you might go about this. What theorems do you know about a tangent? A single tangent. The angle between a tangent and a chord, that's that angle, equals the angle in the alternate segment. That's that one. So let's see if we can find angle DCB. Angle DCB is, oh yes, there's 2 betas here. So it's 180 minus 2 betas. And that's what? Sum of angles of a triangle. Okay. And I think we've done it because that's the same as pi, isn't it? 180 degrees is pi. So now DCB, we can find that, and it's also equal to the angle in the alternate segment. So I've done it around the other way. Angle DCB equals angle BAC, angle between tangent and a chord, something like that. Just abbreviation, so that the person reading it is pointed to a unique theorem. Therefore, angle BAC is pi minus 2 beta, and we would say as required. So I've used each piece of information and got to our solution there. And that's an important strategy. Perhaps start with that, with making sure you're using each piece of information and then working towards the angle you want. All right, let's look at the next part of the question. Prove that AB equals BC. AB equals BC. Now we'll have to go back to the diagram here. So AB equals BC. They don't look equal on our diagram there. AB equals BC. Now, if AB equals BC, how would you show that? We haven't got any known lengths there. But if AB equals BC, you might show that was isosceles, wouldn't you? AB equals BC, if we showed that was isosceles. So come down and put that down here. So when you say that, this would imply that the triangle was isosceles. That's not part of the proof. So you might try to show that the base angles were equal, maybe. So let's have a look at those base angles now, coming up here. So what we want to do, I might just clean this up a bit. What we might want to do is have a look at that angle and that angle. Okay, so now what have we got here? We've got a beta in this one. Okay, and we know that this one is BAC is what? Pi take 2 beta. Okay, so what we can say here is, can we find this angle there, pi take 2 beta, for this one, and can we find that one down there? All right, well, let's have a look and see if we can do it. I think we can, because we've got this angle and this angle in triangle BAC, so we should be able to do sum of angles of a triangle. Let's have a look. So angle BCA equals 180 minus the beta and minus 180 take 2 beta. So therefore, that disappears. Neg beta plus 2 beta equals beta. Now this one is sum angles of the triangle ABC. Okay, so therefore angle BCA equals angle BAC equals pi take 2 beta on the first part. Therefore triangle ABC isosceles equal base angles, and therefore AB equals BC as required. Okay. Now let's go back and mark all of this. Okay, I've got the diagram up the top here still. Let's have a look. We'd give one here for finding that's equal base angles. And probably where's the tangent chord theorem, that one, and the sum of angles of a triangle. Those three important concepts or theorems had to be used for 3 marks. And this one down here, what do we have to do? Sum of angles of that triangle for 1 mark, and then using the idea that it's isosceles because of equal base angles, if you got that in some way. You might have put it differently from what I have there. Okay, so that's out of 5, that one. How did you go? Let's have a look down at the next one now. I didn't put the writing there, I was looking at the figure. Okay, in the figure alongside, have a look. AB is the diameter, now that's important. And AC is a chord, so that's all right. AP is a tangent, just watch that. PQ is parallel to AC, yes, that's marked. See what I'm doing? I'm checking it all off. So we've got to underline these important things. Parallel, okay. All right, now what we want to do is try to use each of those given pieces of information. So let's use the diameter for a start. If AB is the diameter, then angle ACB, this one in here, would have to be 90. Now I'm trying to use that first given piece of information, because that would be angle in semicircle. Okay, angle in a semicircle. Now, what else have we got? We've got the tangent here, this tangent. So what do we know? This is a line through the centre, a diameter. So that's got to be 90 degrees. So angle PAB equals 90. I'm trying to go through each of the given piece of information and use it in the proof. So this is a line from the centre because it's the diameter, line from the centre to point of contact of a tangent is 90 degrees. Okay, what about angle PQC here? Angle PQC, what can we say? This one here, oh, we could use that. Well, what else could we use? We want to show PAQB a concyclic. PAQB. Well, what's the best way? Probably to show that they subtend equal angles on the same side. So we've got PB subtending a 90. Can we show that this one is a 90? Yes, we can. Probably we won't use that one. We'll use BQP. BQP is 90. That's corresponding due to those parallel lines. Okay. Or you could find this one and then get that one, some angles on a straight line. So what have we got now? We can say straight away that PAQB are concyclic because PB subtends equal angles at A and Q. A and Q. So that would do it. That's as required. So let's mark that. I think you've got to have these 3 ideas. Okay. And then make sure you make a mention of the reason for it. All right. Let's go down and look at part B of this one. Hence calculate the size of the angle APB given CAQ is 38. CAQ is 38. Let's tidy this up a bit, all these ticks and stuff here. CAB, hang on, what was it? This is a problem with doing it on screen. CAQ is 38. So I've got to join this. I've got to remember that was 90, that was 90, that was 90. CAQ is 38. Okay, so I've got all the information there. So I want to find angle APB. That's this one up here. So I've got to somehow get up there. Now, what can we say if I've got 38 here? How can I use that? I've got CAQ is 38, and what could we do? Well, we could say here, because at 90, angle AQC is 52, sum of angles of a triangle. So I want to put that down. I'll put it under here. Angle AQC is 52 degrees, sum angles of a triangle. So I've used my 38 in the simplest way I could think of. So that's 52. Now we want to go up here to APQ, isn't it? APB, sorry. So APB up here. Oops, no, APB is actually that one there, isn't it? APB is across there. All right, so what can we do? Well, we can say AQB here, AQB, that's 52, what could we do here with AQB? We could go in here and find that. AQB would be, 128. Now, why would we do that? Angle AQB is 128, some angles straight line. Now, what I'm working up towards is getting up into this position here, APB. Now, it isn't this angle here, it's the whole thing. Now, we could use this, PAQB from part A. It's important to stay on the bus here. It's like a bus trip. PAQB, that's a cyclic quadrilateral. Okay, so if I've got this one, as I just did, then we can say this one's supplementary. So it's important to use that. So here we can say angle APB is 52 degrees, op angles cyclic quadrilateral, which was from part A. We can pinch that. So we've found the size of the angle, which they wanted us to do. So do you get the strategy there? Let's have a look. We came across, we had 38. The easiest way of using it was there. And then I had this angle wrongly marked. It was the big one here. And then we could say, well, if we got this one in here, then you could use opposite angles of a cyclic quadrilateral. Trying to, if you like, take the 38 and work it up towards having some meaning for APB. There's always a strategy. Okay, use each piece of given information and work towards the region of the figure where you need to work. All right, let's mark it down here now. So there are 4 marks there. And I think we've got, 3 here, do you reckon? One for moving it to there, and with a reason there. So that would be out of 7, that question. All right, how are you doing? Let's see, I hope you're getting some marks. I think the important thing, there it is there, we'll put that up above. I think the important thing is you are allowed to use earlier parts, even if you couldn't prove them. And actually think in your mind that questions are often bus trips. You're on a journey and you're supposed to pick up pieces along the way and use them. Okay, let's look at this one. ABC is an equilateral triangle. We'd better underline that and make sure that's on the diagram, and it's not. So we need to put that on the diagram. Parallel to BC, that line is marked parallel. AD is K times BC. Okay, that's all right. That's an interpretation of, in vector land, of parallelism, a scalar multiple of the vector. Okay, so it's got a different length, but it's got the same direction. Let BC equal P, so we better put that down. BC is a vector P, don't confuse it with a parallel line thing. BA is Q. Find BD and AC in terms of P and Q. Well, let's use our given information. AD is K times BC, but they said BC was P, so let's slip it in there. Now we want BD, so BD is what? BD, that's this one here, BD. Let's look at BD as the displacement of B to D. So that will be, take it along here, displace it to A, which is Q, plus AD, which will equal Q plus KP. Okay, get the idea of a vector as a displacement. So instead of going the short way, BD straight from B to D, we can displace B to A and then A to D. The overall displacement is from B to D, so they'll be equal. Okay, go around the back way there. Okay, so that's our first one, what we're required to do. Let's do AC now. AC, we'll just rub some of this out. Got to be careful here. So this was P. So we want A to C down there. So displacing A to C, same as doing it the long way, displace it to B, which is neg P. Oops, sorry, that's Q. I put the wrong thing in there. Oh, I just realised. Okay, so that's neg Q. I rubbed it out and put in the wrong thing. That's neg Q plus P. Take it around the back here. Neg Q plus P, or just we'd usually write it P take Q. So that's the other thing we were asked to do. Find BD and AC in terms of P and Q. And this is usually a precursor or a first step to any vector proof, isn't it? To get everything in terms of some common introduced vectors and then relate them. So that's what we've done there. Let's have a look at part B. And we've got to remember that modulus of absolute value sign is not in there. So, AC and BD are perpendicular. We better have a look at that. So AC, see what I'm doing? I'm trying to use the pieces of given information. AC perpendicular to BD implies AC dot BD is naught. Let's go back and just check. What have we done? They've fed us AC and BD. See, they asked us to do that, so we'll use those. What else haven't we used on the figure? The parallel lines we've used with the KBC, haven't used the equilateral triangle. So we've got to keep that in mind. Haven't needed it yet. Let's come down and see. Now, AC dot BD. Now, we've got to use the result from part A, and AC is P dot Q, P take Q, and we've got to dot that with Q plus K P equals naught. Now that's all logical. Perpendicular means the dot product is 0. That's accepted. That's a definition. And then we put in our vectors in terms of what they asked us in part A. So let's do the next step. Now you've got to know the expansion here. A take B dotted with C plus D or something. Do you know the rule? We're allowed to dot those plus dotting those. So let's do it. This is going to be P dot Q plus P dot KP, take Q dot Q, take Q dot KP equals naught, just replacing those. Okay, so here let's now have a look at this. We'll tidy this up a bit. P dot Q plus K P dot P, take Q dot Q. We can put the K out the front, scalar multiple, and then you've got P dot Q. P dot Q is the same as Q dot P. Now, we've got to do some dot products. And you see here there's a hint. You've got a half in there. Now, some dot products are just going to come out as the length of P squared, or length of Q squared, but these others won't. So what is the definition of this? You can see there are lengths in there, so we want to bring it in. Dot product is the length of one by the length of the other by the cos of the angle. But the angle is 60 degrees, equilateral triangle. 3 angles, each 60. So this is the dot product of P with P is P squared. Length of P squared, length of Q squared. Q dot Q, take K by length of P, length of Q by a half, cos of 60. So there were indicators that we needed to do that. The indicators were working with lengths. We've got a half in here, happened to be the cos of 60. Okay, so we had to go from the dot product notation to unpacking it, length of one, length of the other by the cos of angle, the angle in between. So the reasons here, we've got an equilateral triangle explaining the 60, which will give us a cos of a half, and then P dot P equals length of P squared. They're our basic ideas here. So let's try and make it a little bit neater and say, what have we got? This is a half here, so we've got a half length of P by length of Q plus K times length of P squared, take length of Q squared. You've got to be very patient with these. Take a half K length of P by length of Q, and that equals 0. Now, let's compare it with what we've got up the top, and that comparison is hard. We haven't got any factorisation happening here for the moment. So what we might do is try to write in the same sort of order. And what have we got up here? If you multiply this out, now I think what we'll do is look at expanding or simplifying the to prove line. So we'll expand it all and compare terms. Okay, so we'll have K, here it is up here, K by length of P and then by length of P. So we'll have this. And then we'll have K by length of P by a half Q. So that'll be neg a half Q. So it'll be, we'll put this in here, neg a half K by length of P by length of Q. So that's done K through the whole bracket. Okay. Let's do neg 1 now. Neg 1 by P is neg length of P squared. P by P. And neg 1 by P by neg a half Q would be neg a half P by Q. Like that. It's just getting hard to squeeze it in there. Now what we want to do is to compare those two lines. So refer this as 1 maybe, and let's just have a look. Okay, so if we have a look there, what have we got? Have we got matching terms at all? So we better simplify this a bit more. K by length of P squared and minus a half K by P by Q minus length of P squared minus a half P by Q. Are they looking similar? Yeah, there's a half P by Q. And up here, K P squared. Now we've got minus P squared, and that's got Q there. So let's go back and let's see if we can match them up here. So we've got that term. Now minus a half K by length of P by length of Q. That's that term. Now we might put minus length of Q squared, since length of P equals length of Q, equilateral triangle. Okay, and then we've got our other term here, which is, that should be plus there, shouldn't it? Because up here, let's go up here again. I've messed that up here, because this is neg 1 by negative half PQ. So it's a half plus a half PQ. Yeah, okay. Okay, so you've got to be careful. Lots of things going on here. Okay, so now, which is equivalent to 1? I suppose really, this line up here, I suppose really we should write it in the same order, but the terms match, so that's okay. All right, so how did you go with that? That's fairly challenging, but yeah, it would be an A-type question overall. So let's mark it. Have we marked the first one? No, we haven't marked the first one. So let's have a look at a mark scheme for the first one. I think we can only have one mark for the final answers of those. Okay, and then in this one, more marks. I think we've got one for this, one for the expansion, one for putting in the halves to get to basically this step or step 1, this idea here, and then the expansion. So I'll probably only leave it at 4, this expansion, either of those two. Give you 1 mark for that. Okay, fairly hard marks to get those ones there. So this question is out of a total of what? 2 is 6. So part A is worth 2 and part B is worth 4. A lot of care needed there. Tricky stuff. You want to try and remember some of those tricks. Let's have a look at question 4. The diagram below shows 2 diameters. Ooh, that's going to be important. These are both diameters, so that's the centre of the circle. That could be interesting. Prove that PQRS is a rectangle. So we better draw in PQRS. Okay. This here. Now, what's the property of a rectangle that you think you might be able to use? Well, opposite angles are 90 degrees there would do it. And I think that's indicated because we got diameters. So I want to jump right into diameters and say, well, angle PQR, I want to use the given information. There is a system. Squeeze all you can with theorems out of the given information. PQR is 90, angle in semicircle, right? Because PR is a diameter. Don't have to put that. Okay, and what's the other one? So that's that angle. I think PSR, do the opposite one over here. Angle PSR is also 90, same reason, and in semicircle. This time Q, PR diameter again. Okay, so therefore, what you've got is a rectangle, PQRS, a rectangle, and you could sort of justify that by saying just opposite angles are 90. But what you can say is that the 180 is split between these two, and they are also 90. So maybe we should put that in, that QS QS is a diameter, and so SPQ, we might put that in, SPQ equals 90 equals SRQ, angle in the semicircle, the other side there. Okay, for that other diameter, they might put that. I reckon we'll only give 2 marks there for showing those opposite angles are both 90. But it would be good to have this there as well. So see what you think about that. But let's have a look at part B. The acute angle between the diameters, here it is here, is theta. Right, so it's the same as what we had before. So we know it's a rectangle. All of these are actually going to be 90. Up to the top there. Okay, now we want an area. Okay, the area of area of rectangle PQRS, what would it be? Well, it's going to be double this, isn't it? So what's the area of those two triangles? Let's put here area triangle, that's POS because that's the centre, plus area triangle POQ. Okay, there's symmetry there in that rectangle, so it's twice that. Okay, POS, that's half the product of PO by OS by the sine of theta. The area of the other one up here is half the product of PO by OQ by sine of 180 minus theta. Because this angle in here, some angles on a straight line, 180 take theta, some angle straight line. Okay, so what have we got? Doubling everything, we've got PO, which is an R. It's a radius, isn't it? PO, OS are both radii, sine theta, and it's doubling that, plus doubling this one. PO by RQ, PO by OQ are both radii, and the sine of 180 minus theta is the same as the sine of theta. Better put that. Sine 180 minus theta equals sine of theta. So this is r squared sine theta plus r squared sine theta, which is 2r squared sine theta, 2 of them. And that's as required. So let's mark that as well. I reckon probably 1 for showing you what you're doing, 1 for correctly doing that, and 1 for tidying up with the radii. So that's out of 3, and the one up here was out of 2. So the whole question, give yourself a mark out of 5. How are you going there? Getting a few, I hope? 2 questions to go. Let's see how we go with those now. So let's come down and read it first of all. In the acute angle triangle ABC, perpendiculars, what's that? AP and CQ. All right, better put those in. AP and CQ. There. Okay, check that all the given information is marked on the diagram, because now what we're going to do is to start using it. All right, so let's look at the first one, BPZQ. BPZQ, that's this one here, BP, that there, that little quadrilateral, we have to show is cyclic. Well, it's not subtending any angles, there's nothing like that, so we'll probably go for opposite angles, and I think you've got it because you've got these things here, angle BQZ is 90 because it's perpendicular. CQ perpendicular to AB, that was given. Angle BPZ is 90 because AP was perpendicular to BC. Okay, come down a bit here, run out of room. Therefore, BPZQ is cyclic. Oh, sorry about that. Let's just stop that for a minute. So we've got BPZQ is cyclic, op angles supplementary. Okay. So let's do ACPQ. Let's have a look at the diagram again now. ACPQ. Oh, well, that's self-evident, isn't it? We can go straight to that because we've got those two subtended by AC on the same side. Okay, so we can say straight up ACPQ cyclic, AC subtends 90 at P and Q. And then we'll put as required down here. Okay. Bit scratchy on the screen there. Okay, so what do you reckon that's worth? I think we've got to give 3 and then 1. Okay, the second cyclic quadrilateral is a bit easier because it's given to us that they are 90, they're perpendiculars. The interesting thing to note here, might keep in the back of your mind, that if this is subtending 90, then what that is, it means it's a diameter, isn't it? There's only 1/4 of a circle that subtends 90 at the circumference. Okay, and that's a diameter. So keep that in mind. That could be useful a bit later on, perhaps. Okay, let's go on. Angle PAC, we've got to prove that angle PAC, let's have a look at that. PAC is this angle, equals ZBP. Okay, so let's have a look at what we could do there. We'll just come down here. I'll try and keep it in here, I think. Let angle ZBP, let that be alpha, or I call it alpha 1 maybe. So let's have a look. Alpha 1. ZBP, hang on, ZBP, we've got to write that in. I'll get rid of some of this, I think. We've got to remember they're 90. ZBP is alpha 1. Let's call that alpha 1. And is there something equal to that? Now, we've got some cyclic quadrilaterals, so we could go PQZ. This one in here is alpha 2 because of that cyclic quadrilateral. And then, can we get up to the big one? Oh yes, because then in the big cyclic quadrilateral, we've got subtended by PC, so that'll be alpha 3. We shouldn't do all that at once, we should try and write it down. So, angle PQZ would be alpha 2, subtended, same arc, and this is from part 1, because they're cyclic quadrilaterals, and PAC is alpha 3, subtended by the same arc, again from 1. Okay, so therefore you can say PAC angle equals ZBP, and that's as required. Okay, let's just check that so you understand it. What we did, I'll get rid of all this again, what we did was to say we wanted that angle, call it alpha 1, because this was cyclic, this little one in here, PQZ was alpha 2, And then because this was cyclic, because they're subtended by that arc, because this was cyclic, that now subtends that one and an alpha 3 up here. So popping from one cyclic quadrilateral to the other there. So that was hard to see, I think. All right, let's go on to part B and have a look. Okay, so it's the same figure again. So let's go and mark in the things that we had before. Like that, and we had, what did we have here? We had this one here. We've got to mark them in carefully. This was alpha, and this was alpha. And what other angle we had? We had the one, let's go here, PQZ and ZBP. PQZ. We actually had that one as alpha as well. I don't know whether they're all going to help us here, all that stuff is going to help us again, but let's have a look. What we've got to do is prove that LBP equals ZBP. Okay, well, let's have a look at ZBP. ZBP is that one there, and LBP was alpha. Well, we called LBP alpha from before. So let's have a look at what we've gone and see if we can match them up. All right, so let's have a look and we'll write down some things here. Let's start with angle ZBP. ZBP was this one in here. That was alpha from part A. Okay. Angle PAC was alpha from part A. Okay, let's go and look at that, PAC, that we were asked to show those things. So now, what can we say? Angle LBP, I put that in, we didn't show that from before. LBP will be alpha. LBP will be alpha. Why will that be alpha? Let's have a look at it. LBP is subtended by LC, which also subtends that alpha up there. So again, subtended by the same arc. In the bigger cyclic quadrilateral there. Okay, so therefore we can say angle LBP equals angle ZBP. All right, so fairly complicated therefore, but not too bad. We've only got 2 marks here really. We've got to pick that up from A, I think, and then show that it's the LBP is subtended by the same arc there. All right, using the cyclic quadrilaterals from part A. So just remember the bus trip. You've got to build up your properties of the problem or the figure. Okay, let's have a look at KB equals BL. This is always problematic, showing 2 things are equal. KB equals BL. I'll put it in. KB equals BL. Let's just get rid of this. KB equals BL. Okay, so KB equals BL. How would you show it? Well, we can't really put in any lengths. There's no lengths mentioned. So if KB equals BL, we might go for isosceles triangle. Okay, something like that. Or, yeah, that would be the best way, wouldn't it? So what have we got? Let's try and work on the stuff that we've got, building up our bus trip. We've just shown that. So can we use it, thinking that it probably leads on? Well, let's have a look at the triangle BZL. In triangle BZL, we've got those two angles equal here. All right, BZL, and bisects a vertical angle and it's perpendicular to the base. Vertical angle bisected by line perpendicular to the base. Therefore, triangle BZL isosceles. It's a converse of the theorem, isn't it? In a isosceles triangle, the line drawn perpendicular base bisects the base and bisects the vertical angle. Okay, so therefore, what can we say? It's got two equal sides. BZ equals BL. So we're saying, let's just get rid of that, BZ equals BL because of that property happening there. BZ equals BL. Shouldn't do that. Keep doing it. Okay, so we've got an isosceles triangle there. Now we want KB to be BL. KB's over here. Can we show that that's isosceles? If we can, then you can say these two sides are equal, and we've gone from that equals that equals that. So let's have a look. So here we can do the same thing in that triangle. So we could say, let's put similarly, angle KBQ equals angle QBZ. Let's just look at that now. KBQ equals QBZ, those two are equal, and you've got the same theorem again. So therefore triangle KBZ isosceles, converse of the median theorem. Okay, therefore KB equals BZ, and therefore KB equals BL, because they're both equal to BZ. I've got to put a reason in here. KB equals BZ, equal sides. Isosceles triangle. All right, so I reckon, what do we need to do? I think we need to look at the converse of the theorem up there, and then stating that this one is also isosceles, giving that out of 4. So what is the overall mark for that question? That was worth 4, we said. I haven't got any marks down here. Let's just see what that's worth. So that'd be worth 2, wouldn't it? So that's 6, and then what have we got? 8, 9, 10. We have 10 marks. So 6 and 4. So that whole question would be out of 10. We'll check the addition of all these. Make sure they come to 38 in a minute. So that's 6 and 4. How are you going? Getting some? There's some hard questions here, actually. Got to have a strategy. Make sure you use all the given information at each point. Okay, here's a question. Let's have a look and make sure everything's on the diagram. The midpoint, that's a midpoint, it's marked that way. Got to prove this. They've introduced the vectors, yeah, and they've given you a hint that if you're looking at squares of sides, you could be looking at the square of the length. You would be looking at the square of the length, which comes out of dot products. So that's a clue. So they're giving you an idea, go for dot products, mate. Go for dot products. So let's have a look at what we might go for. All right, well, what we need to do is to look at trying to do something with one of these two sides. We want to prove this. So I'd like to start with a more complicated side. I'm going to try and start with that and end up with this. Okay, so what do I want to do? I want to work out AB. in P's and Q's. So I'm going to start there and get these two and see if we can get something happening there. Okay, so AB, this one along here, displace A to B. That would be the same as going around the back way. Displace A to O, which would be neg A, and then down to B is plus B, or we normally simplify that as B take A, putting the negative second. Therefore AM, because we're going to need that for OM in a minute, all right, come over here, we've got to do OM. So AM is going to be a half B take A. More of the dot product stuff. Let's get OM, because that's this line we're trying to start with this and end up with the left-hand side. So OM, displacing O to M, is the same as going A plus AM. Okay, so it's A plus a half of B take A. Okay. So now we've got that, we might start with the right-hand side, which is 2 OM squared plus a half AB squared, which is now 2. Now, what are we going to do? The square they've given us in is the size of the dot product. So let's do OM dotted with itself. So that's A. Well, hang on. Oh, this is here. Let's simplify it. I don't like the look of that. That's A plus a half B take a half A, isn't it? Which is a half A plus B, something like that. Let's do that. All right, simplify it. Okay, so OM squared is a half A plus B dotted with a half A plus B, looking a bit messy here at the moment, and that's OM squared. So we've got 2 of them. Now we need a half AB squared, which is AB dotted with itself. Boy, what a mess. Okay, they told us to use the dot product to get the square of the length. So let's do that. All right, so let's have a look at what that comes to. So let's leave the 2 out the front and bring out a half by a half. Scalar multiples is a quarter, and then we'll dot A plus B by A plus B. So it's A dot A plus A dot B plus, now do these, B dot A plus B dot B. That's 2 OM squared. Just doing that rule for the product of 2 dot products. Now let's do this one over here. B dot B. Okay, you've got to be neat here. Minus B dot A. And this one, take A dot B, neg by negative positive A dot A. Oh well, okay, so this is 2 by a quarter is a half. Let's go through this bracket by multiplying them all by a half. So it's what? A dot A is length of A squared, and well, what have we got? B dot B. We'll put this up the front. No, we'll do these two first. Plus 2 times A dot B plus, oops, 2 times A dot B, that's right, plus length of B squared. Got to be careful here. Length of B dot B, length of B squared, take 2a dot b plus length of a squared. Wow. Okay, so what's this come to? It's half now. We've got need more room here. So it's a half length of a squared plus a half of this is just one lot of a dot b plus a half length of b squared plus in this bracket a half length of b squared, half by -2, -1 a dot b plus a half length of a squared. Okay, let's collect up the length of a squared. So there's half there and half there. That's one lot of a squared, and then b squared, half plus a half, one lot of b squared plus a dot b, take a dot b, and they go out. So that's made it neat. So it equals length of a squared plus length of b squared. And I think that's it, isn't it? Length of a, which is OA squared plus OB squared. So we can put that equals, just come down a bit more, equals length of OA, I'll just put OA squared, because it's not a vector as they've written it, plus OB squared as required. So we've used their hint to go to the most difficult part of the expression and simplify it to the simplest part. Let's mark it now. I think there's one mark for getting AM and OM in terms of the given vectors A and B. And then one for getting this line before simplifying, and this line before simplifying. And then there's probably one for getting somewhere down here, the expansion, and then one for the simplification, something about here, I would say. So 5 marks for that one. What's out of 5? Okay, fairly challenging, those vector proofs with dot products. You've got to know the rules there for the dot product. Let's check the addition. Let's go back up now. So there's 5, 15 for that question, the 2 parts, 20 for that question, over up to that question, 26, 33, and 5. Okay, so 38 marks. How did you go? That is a pretty challenging stuff in actual fact. All right, well, good luck. Keep the revision up, ready for the actual test. But for now, good luck, and I'll catch you a bit later on.